Steinhauer here. Welcome back. We're starting now our discussion of Chapter 6, Astronomical Instruments, which is basically a discussion of telescopes and why they're useful and where we put them and what they do for astronomers. So let's get started. How do telescopes work? What are they? Why are they important? Well, anything, it turns out, that can bend light can make an image. And so one way to bend light is with glass. If you have a piece of glass and you shape it in exactly the right way, then any beam that is incident upon that lens will be focused to exactly the same point. That's coming from the same direction will be focused to exactly the same point. And this, if you have light coming in from a slightly different direction, let's say in this direction, all of these lights will be focused to a slightly different point. And this will make an image of whatever the lens is pointed at this point where the focal plane is. And so in this way, you can make an image, and therefore you can use it as an astronomical telescope. In fact, this is the way your eye works. Your eye has a lens in it, and this is the back of your eye here. The image is formed on the back of your eye. You have detectors in the back of your eye that turn those light patterns into electrical signals that are transmitted to your brain so that you can see what's going on. Telescopes work in very much the same way. There's two basic designs for how a telescope can work. One uses the lenses that I was just talking about. So you have a lens up here at the top that directs the light back down into usually another lens down here so that you can actually put your eye here and actually look and see what's there. You can also bend light, not only with pieces of glass, but with mirrors. And mirrors work much the same way. Any incident light that's coming in will get reflected to a single point. In this particular case, you need to reflect that out to be able to see it on the side of your telescope. The problem with a mirror, there's lots of advantages to having mirrors. You can make them much bigger. You can support them from the back. They don't suffer some of the aberrations that lenses do. The problem is you are directing the light back up to where it came. So there's always some sort of secondary thing that you need here. You're going to be blocking some of the light that's coming in to redirect the light either out the side of the telescope or through the back of the telescope. There's different ways to do this, but you're always going to miss some of this light here from a reflector telescope. This won't cause a hole in your image. It's just that you'll be blocking some of the light from all parts of your image simultaneously. So you might be more familiar with these refracting telescopes that use lenses, but there's a limit on how big you can make those. In fact, this is the largest refracting telescope in the world. There's not much scale here, but this is the Yerkes Observatory in southern Wisconsin near Chicago, and it has a primary mirror diameter of 40 inches. And one of the problems with these big refracting telescopes is that you have to build them very long. And part of the reason for that is because lenses, as you make them bigger and bigger, become very, very heavy. And you have to support them on the outside where they're the thinnest. And so that means that they have to be fairly flat. And fairly flat means that you're not bending the light very much. And so you need a very long tube in order to have that light actually come to a focus down here at the bottom. So this is the Yerkes Observatory. As I said, it was built in 1897. That is still the largest refracting telescope in the world. And the lens at the top of this thing is 40 inches in diameter and weighs almost 500 pounds. This is an enormously heavy, bulky thing. And they had to make this tube gigantic just to be able to have the lens long enough, the focal length long enough that they could actually get it to come to focus down here at the bottom. So no modern astronomical telescopes. There are plenty of telescopes in the world that are bigger than 40 inches, but they all use mirrors instead of lenses. And so all modern telescopes, all modern professional telescopes using mirrors instead of lenses. And here's an example. You can see way bigger than 40 inches. Here's a person down here, and this is, I believe, an 8-meter across diameter, 8 meters across, right, diameter mirror. And so these can be made much larger because you can support them from behind, and they can be very thin. And you can just shape them to whatever shape you want and don't need to worry. So this is probably more than 500 pounds, but not a lot more than 500 pounds. And it's way, way bigger than the refracting telescope, the biggest refracting telescope in the world. This is an example of one of the biggest single mirror telescopes in the world, 8 meters in diameter. It turns out that it's kind of hard to build single mirrors that are that big, but we've gotten around that problem by building mirrors with segments. So this is an example of, we're looking at the Keck telescope. The Keck telescopes are on Mauna Kea in Hawaii. I don't know if you can see this very well, but it's not a single mirror. And for scale, this is even bigger than the last telescope I were looking at. This is about 10 meters across from one side to the other. So it's even bigger than the last one. And they manage to do that by splitting it up and making it a bunch of smaller mirrors. And I don't know if you can see these hexagonal segments here. These are all individual mirrors, mosaiced together to give you the surface area of a single 10-meter diameter mirror. Okay, so why do we want to build telescopes? What do they do for us? It turns out there's 3 powers of a telescope. There's 3 things that a telescope does for you to help you out. One is magnification. Telescopes can make things look larger. One is light collecting area. Telescopes, the bigger a telescope you have, the more light you can gather from a distant source in a shorter amount of time. And the third is angular resolution. Telescopes the bigger the telescope, the better the theoretical angular resolution, meaning you can distinguish between objects that are closer and closer together. The smaller the angular resolution, the better. The smaller you can see 2 objects that are closer together and be distinguished as 2 separate objects, say stars. So those are the powers. That is what a telescope gets you. So here's a question for you. Which of these 3 powers do you think is least important to astronomers? Magnification, light collecting area, or angular resolution? Go ahead and make a guess. It turns out that most people say magnification because that's sort of the first thing you think of. How big can we make something look? And if you're a pirate on the open sea and you want to know whose flag is flying on a ship that's in the distance, magnification is important because you need to be able to resolve it in your eye if it's very far away. It turns out that, though, is the least important aspect to astronomers. In fact, most telescopes don't magnify much at all, even the very large ones. We are much more interested in light collecting area, being able to see very faint things, and angular resolution, being able to resolve more and more important things. In fact, magnification does you no good if you don't simultaneously increase your angular resolution and be able to distinguish things that are close together. So let's hone in on B and C here and learn some more about how light collecting area works and how angular resolution works. So bigger is better. I already mentioned that, but it's not just an astronomer's ego at play. The bigger the telescope, the more light you gather. It's sort of like light from the object that you're interested in is constantly washing over the Earth. And the bigger you can make your bucket to collect that light, the more of it you will get and the better the data you will have, the more accurate your data will be in terms of how bright that object actually is. So simply making a bigger telescope will simply collect more of this light that's streaming down and allow you to see that object better and clearer. So that's the light collecting area part of a telescope. The bigger you make your telescope, the more light you get and the fainter an object that you can actually see with that telescope. And for even bright objects, the less time you have to spend getting the same amount of, let's say, signal for that particular object. So bigger is better, and light gathering power is probably the most important aspect of a telescope for an astronomer. We just want to be able to see as faint as we can possibly see. Angular resolution also helps a lot. Here's an example of the same galaxy with 4 different angular resolutions. And you can see how much better your understanding and view of this object gets as you go towards better and better angular resolution. For this one up in the upper left, you can kind of see some fuzzy patches. You can kind of make out that there's some knots. But by the time you get to D, you can now start making individual assessments about each one of these spiral arms, and you can just understand a lot better what's going on with the galaxy, the better your angular resolution gets. So this is a good example of what angular resolution is and why it's so helpful and important to astronomers. And it turns out that making your telescope bigger not only gives you more light, which we're not even illustrating here in this diagram, but it also makes your angular resolution better. The bigger your telescope, the better the theoretical angular resolution is for your telescope. So bigger is always better for astronomical telescopes. Okay, let's hone in on light collecting area though for a little bit. Light gathering power, LGP, as I'll abbreviate it, scales as the area, the surface area of the primary light gathering instrument. Whether that's a lens or a mirror doesn't really matter. And the area, the surface area of that, since these things are almost always circular in diameter, scales as the diameter of that object squared, because LGP, light gathering power, is really just area. An area of a circle is pi times the radius squared. And we almost always talk about these telescopes being the diameter, and the diameter is, of course, just twice the radius. So the area of a lens or mirror is pi times its diameter over 2 quantity squared. And that is the light gathering power. And I say here that 40-inch refractor in Yerkes was nice, but now we're building telescopes that are about 10 meters in diameter, and they are breaking ground now on the next generation of telescopes that will be about 30 meters in diameter. And that's going to be game changer for how we can do astronomy. So here's a quick question. Let's try to test this equation out and see how it works. Here's a thought question. How does the collecting area or the light gathering power of a 10-meter telescope compare with that of a 2-meter telescope? You can pause, try to work this out for yourself, and then we'll come back and do it together. Okay, let's do this together. We know that LGP is pi times diameter over 2. It's not a very good diameter. Pi is pi times diameter over 2 quantity squared. That is the surface area of a circle. So this is going to be simplest if we take a ratio. So for instance, if I've got 2 telescopes and I want to know what their ratio of light gathering power is, that's basically what I'm asking. What is the ratio of the light gathering power of a 10-meter telescope to a 2-meter telescope? And so we can set this up as a ratio, LGP of telescope 1 over LGP of telescope 2, light gathering powers. We have pi times D1 over 2, quantity squared, divided by pi times D2 over 2, quantity squared. And this is where you can see the power of ratios comes into full fruition. We've got a pi on top and bottom. Those cancel out. We've got, and now we can use a mathematical trick to take this square on top and this square on bottom and combine them. So you can take D1 over 2 and square it, and then divide it by D2 over 2 and then square it. Or you can simply take D1 over 2 divided by D2 over 2 and take that quantity squared. Those two things are identical. So let's bring all of this inside the square. Let me come down here. again, the ratio of light gathering powers of these two telescopes is D1 over 2 quantity divided by D2 over 2, all of that quantity squared. And now you can see more things cancel out. I've got a 2 in the denominator down here and a 2 in the denominator down there. Those also cancel out. And this becomes a much simpler relationship, which is simply that the ratio of the light gathering powers is simply the ratio of the diameters quantity squared. And that works for any two telescopes that you are comparing. All you need to do is make sure that D1 and D2 are in the same unit so that they cancel out, and then you square that, and then that will be the ratio of the light gathering powers of these two telescopes. So let's think about it. Let's actually plug it in. Let's say we want the ratio of the 10 meter to the 2 meter light gathering power. So we need to put the 10 meter on top and the 2 meter on bottom. This is 10 meters divided by 2 meters, quantity squared. 10 meters divided by 2 meters is just 5. The meters cancel out. This is a unitless number now. And this is just 5 squared. And this is 25. So a 10 meter telescope will have a light gathering power that is 25 times greater than that of a 2 meter telescope. And for these light gathering powers, we're almost always comparing telescopes when we're doing these calculations. So that's should be an easy calculation to make. The light gathering power is simply the ratio of the diameters quantity squared. So those 30 meter telescopes I was looking at before are 3 times larger than the current largest telescopes, which are 10 meters. And so they will have a light gathering power that is 3 squared, or 9 times the current best telescopes out there. The next generation of telescopes will be almost 10 times better, have almost 10 times better light gathering power than the best telescopes we have now. And that's going to be a significant upgrade to our capabilities in astronomy. Okay, I'll stop there for now. See you next time.